Welcome to video 4 from chapter 3. In this video, we will look at correlational research as well as developmental designs. So in correlational research, there is no treatment like there is in an experiment. You just are interested in whether or not variables are related to one another and how strongly they're related and you know and the specific direction or nature of the relationship. So in correlational research, what we do is we collect variables that we're interested in and you compare them two at a time. So suppose, just to looking at the top left for now, suppose I'm interested in some of the factors that affect test grades for students. So I collect a variable of how many hours each subject is studying during the week. And this may be collected in various ways. Most likely you would collect this data with self-reports where the subjects record their studying times during the week. And then we're also interested in whether or not drinking during the week affects test scores. And so we would have subjects record how many hours they are drinking alcohol per week. And then we also, of course, we collect their test scores. So whenever you perform a correlation, you take a pair of variables at a time. It's always two variables that you have data for. And there is a statistical technique that compares the two sets of numbers against each other to see if there's a relationship. Out of this statistical research, you arrive at what's called a correlation coefficient. It's the numbers that you see in green there. These correlation coefficients range anywhere from -1 up to +1. Ignoring the sign for a moment, positive versus negative, the closer the number is to 1 or to -1, the stronger the relationship. So in these two examples in green, you can see that the number of hours studying per week is related to test grade with a correlation coefficient of 0.35. The number of hours of drinking per week and the test scores are related with a correlation coefficient of -0.8. Because 0.8 is closer to 1 than 0.35 is, and once again, you just ignore the sign when you look at strength. So 0.8 is higher than 0.35. We know this tells us that the number of hours spent drinking alcohol per week is more strongly related to test grades than the number of hours studying per week. And that 0.8 is very close, that -0.8 is very close to -1, relatively speaking. And this tells us it's a very strong relationship, that the number of hours of drinking really is very strongly related to test grades. The 0.35 is also statistically significant, but it's not as strong or as closely related as the time spent drinking alcohol. Now, one of them is positive and one's negative. The sign of the relationship, positive versus negative, tells us how the two variables are related. A positive correlation means that the numbers go in the same direction, meaning that high numbers go with high numbers, low numbers go with low numbers. So this, when we see positive 0.35, it means the more hours studying per week, the higher the test grades tend to be. The lower number of hours studying, the lower the test grade. So positive just means same direction, high numbers with high numbers, low numbers with low numbers. The negative sign with the -0.8 means that the directions reversed. That higher numbers go with lower numbers. So the more hours drinking per week, the higher that goes, the lower the test grade tends to be, which is what you would expect. If you the lower the number of hours drinking, the higher the test score. So correlation coefficients tell us two things: the strength of a relationship, the closer to one or -1, the stronger the relationship, and it tells us the direction of the relationship. Positive means the same direction with high numbers going with high numbers. Negative means the opposite direction. High numbers go with low numbers. If you have a correlation close to zero, it means that the two variables are not related. So suppose I was to measure all of your IQs and all of your shoe sizes. Most likely I would get a correlation close to zero, because there's no reason to suspect that people that have bigger feet have either better or worse IQs, higher or lower IQs. Most likely your foot size has nothing to do with your IQ. So we'd probably end up with a correlation very close to zero. It won't be exactly zero, but anything that's close to zero is a non-relationship. There are statistical tests to tell you whether or not the specific correlation coefficient you arrive at is statistically significant or not. Oh yeah, I will get to the rest of this slide in a moment. Just to backtrack, um, so in a correlation coefficient, we're just collecting data. We're not affecting um, the subjects at all. So unlike, in an experiment where we have a treatment and we do something different in one group versus another, in correlation coefficients, in correlational studies, there is no, groups assigned. You're just collecting data from a large number of subjects and comparing the different variables against each other. Because we have no control over the variables in the study, over any of the variables in the study, we're just measuring them. We cannot infer causality between the variables. We can't say that one variable causes another. This is true of any correlational research. It is kind of one of the most basic rules of correlations. You cannot say that one of the variables causes the other, no matter how strong the relationship may appear to be. Now, the reason that you can't determine that one variable causes another is that there's always a number of possibilities that may be causing the correlation. We're going to look at those now. So in this example on the right side, you see that the amount of TV viewing is positively correlated with teenage obesity. I'm not given a specific number, but it's positively correlated. So we know it's a positive correlation, meaning that more TV viewing will go with more obesity. Lower hours of TV viewing will go with less obesity. Now, we may just want to assume, hey, these things are related, so it must be that TV viewing is causing children or adolescents to become more obese. But once again, we cannot assume that. We cannot assume a cause and effect relation. One problem is that there's often what's called the directionality problem. We can't say which variable is causing which in a correlation. Many times, both possibilities are equally likely, or at least possible. So we don't know if A causes B or does B cause A, that leads to them being correlated. So I said that maybe we would assume that TV viewing causes obesity, but it's also possible that people that are heavier to begin with, this causes them to sit around and watch more TV because they less likely to want to be active if they have extra weight, and so it could be that the obesity, that the weight that a person is, causes the amount of TV viewing, and that heavier people sit around more and watch more TV, and people that are less heavy, are more active and have less time for TV. So we don't know which way the direction goes, whether the TV viewing is causing the obesity or the obesity is causing TV viewing. There's no way to tell from running a correlational study. All we know is that somehow these variables are related. There's also what's called the third variable problem. You can see it pictured there on the left. It may be that neither A nor B causes any changes in the other. They may not have a causal relationship where one affects the other. There may be some third variable that causes the relationship between A and B, even though they're not affecting each other. And this is always one possibility in any correlation, that there's something else that's relating the variables. So one possibility in this example is socioeconomic status. We know from other research that people that are of a lower socioeconomic status tend to watch more TV. We also know from previous studies that people of a lower socioeconomic status also tend to have a higher probability of being obese. So it may be that the socioeconomic status of the subjects are causing the variables of TV viewing and obesity to be related. People that have a higher SES tend to have less TV viewing and less obesity. People of a lower SES have more TV viewing and more obesity. So the TV viewing may not be having anything to do with the obesity. The obesity has nothing to do with the amount of TV viewing. They just end up being related because of socioeconomic status. And there's other possible third variables as well that you might be able to think of that would affect both of them. And then there's always a fourth possibility as well, and that could be random chance. Sometimes you can collect, data from a number of subjects and on two variables, and they end up appearing to be correlated, and it's just, a statistical anomaly that you happen to, pick the right people where there appeared to be a relationship, but there isn't really. And so that's always a possibility too. And this last possibility, you could discover if you were to replicate the experiment. You may, the next time you run it, you may find that there's no correlation. It comes close to zero. And okay, so because there are these four possibilities, there was no way to determine which one is the correct reason for the correlation. And this is why we can never decide that, hey, I found a correlation, so I know that one thing causes another. You could run experiments. You could go back to the experimental method to try to determine which one of these possibilities is the accurate one. Okay, so that's correlations. So just keep in mind that it's a way to see if variables are related, how strongly they're related, and the nature of the relationship, positive or negative. And the more strongly related the variables are, the more predictive they are of each other. So going back to our first two examples, if I know how much somebody drinks per week, and because it's strongly related to test grade, I would be able to make a fairly good prediction about what their test score will be. If I know how many hours they study per week, well, that's not as strongly related. I would have some idea of what their test grade might be, but my predictions won't be as accurate. In similar ways, they use your SAT scores to predict first-year college GPA. Those two things are correlated. People that score higher on SAT scores tend to have higher first-year college GPAs. And lower goes with lower. Okay. In developmental psychology, we have some special research designs um, that has to do with development. Uh, we are interested in developmental psychology and in how people change over time, how they develop over time, whether it's children or adolescents or adults in lifespan developmental psychology. And so we often use studies that will track and test the same subjects over time. In this particular study, and I'm not concerned with the actual what they were actually looking at here. I'm just using this graph as an example. You can see that they collected subjects that were 6 years of age, and they followed these subjects until they were 12 years of age, recording hyperactivity levels, along the way. Perhaps, once a year they would test them. And so this study, is spanning 6 years, and it would take 6 years to run this. So we call this study here a longitudinal design. So this is one of the specific developmental designs used in developmental psychology. You 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 start with subjects at one particular age, and you follow them and test them at various ages in the future. It may be, like in this example, just a couple of years. In this case, they're just testing six-year-olds, and then they're retesting them at 8 years of age to see how much they've changed over 2 years. Or it can be very long term. There are lifetime developmental studies that go on where they start with infants and they follow them until they die. I mean, it's obviously a research design that gets passed from one researcher to another over time, and it'll be run by an institution rather than a single person. And so those are very interesting studies. There's always some longitudinal lifespan longitudinal groups going on in different colleges or universities. And when researchers are looking to study some particular age changes, they often look for a study that's already ongoing. Rather than start their own, they may discover, oh, the Seattle longitudinal study, they have subjects that are just turning 5, and I'm interested in studying the age range of 5 to 10. And so I would ask their permission to include my, test items in their longitudinal study. And this is the way these lifespan studies work. Different researchers kind of tap into them and use their subjects to study what they want to at different points of the lifespan. Okay, just to kind of graph it out here. Here's an example, just looking at the top 3 numbers of a longitudinal design. So let's say last year in 2020, I collected subjects that were 5 years of age, and I tested them on some measure. Maybe I'm just looking at, I don't know, how certain mathematics skills change between 5 and 11 years of age. So I collect the 5-year-olds, once again, just looking along the top. I test them on some items. I wait 3 years. I want to see how they do at 8 years of age. I wait 3 more years and test them at 11. So here I see how a group of individuals, how their particular mathematics skills change from 5 to 11. Excuse me. Longitudinal studies are considered powerful studies because you're tracking, you're comparing the same subjects against themselves. So, it's not like I have a different group of subjects at each age. I'm seeing the same subjects over and over again. And so I can see individual patterns, like perhaps, most of the subjects improved in the skill from 8 to 11, but maybe there was a small group of subjects that went downwards on that particular skill. And I might be very interested in, well, what's special about those people. So like I can see individual patterns um, of if subjects like behave differently than the majority of the group. And sometimes the individual differences are very interesting to study. The second developmental design is called cross-sectional research. Once again, I'm interested in the development of a particular skill, let's say, um, but I don't want to wait. I'm just going to go back to the diagram. I don't want to wait 6 years from 5 to my subjects turn 11, and I get my final results in 2026. I want to do it all at once and find out how the skill changes from between 5 and 11. So instead of waiting 6 years, maybe all at once in 1 year, I collect 3 different groups of subjects. You can see it pictured on the left. I get a group of 5-year-olds, a group of 8-year-olds, and a group of 11-year-olds, and I compare them on whatever particular behavior I'm interested in comparing. And I see how how the how the 8-year-olds are different than the 5-year-olds, and how the 11-year-olds are different from the 8-year-olds. And I do it all at once, so it's much quicker. It's saves years of research. Um, but there are potential problems with cross-sectional studies, and you're comparing. You're comparing different people against each other, and there's something that may happen called a cohort effect. Cohort, COHORT, cohort effects can exist if the different groups have had different life experiences, meaning that maybe something changed um, during the course of something changed during the course of some of these subjects' lives that affected some of them, but not others. And let me give you a simple example. Imagine I'm testing computer skills, and I'm doing a cross-sectional study. And just to make it real obvious, let's just say I collect a group of 10-year-olds and I measure their computer skills. I collect a group of 40-year-olds, I measure their computer skills, and a group of 70-year-olds and measure their computer skills. And then, surprisingly, I look at the scores from each group, and it turns out that the 10-year-olds perform a little bit better than the 40-year-olds, and they perform quite a bit better than the 70-year-olds. And so my data seems to suggest that computer skills decline somewhere from between the ages of 10 and 40, and then again between 40 and 70. So kind of like, it looks like, you lose your computer skills as you go from childhood to middle age. Well, that doesn't make a lot of sense. The reason the 40-year-olds might be scoring a little less than the 10-year-olds, a little lower, is because of a cohort effect, because they've had different life experiences. Back when those 40-year-olds were in school, this would have been like, let's say around 1980, computers, microcomputers were just coming onto the scene, and they weren't very good. Schools did not have computers to teach students. When I was in high school in 80? It was like 1981, I think, when my school got their first computer, an Apple computer, and it wasn't used in any classes, but you could sign up for time after school, which is when I started learning computer programming, because I was a nerd and wanted to stick around and learn about this new computer. And so the people that were growing up at that time, had no experience with computers, and so those are our 40-year-olds now. Well, some of them have gone through life with like no computer training, and so they just know the basics. Whereas our 10-year-olds now, they have computers in every classroom. They start learning from a young age, they all have computers at home. I mean, like, they've grown up in a very different world. And if you think about the 70-year-olds, no wonder like they're going to be the lowest. They went most of their lives before computers were available. And so anyways, cohort effects is that something has changed in society, or there's been some kind of historical change that affected the groups differently. So we're not really seeing the progression of ages. Like, we're not seeing what really happens to computer skills between 10 and 40. We're just seeing the effects of a cohort effect, that life has changed. The 10-year-olds are growing up in a very different world than the 40-year-olds grew up when they were children. Okay, so this is one of the potential problems with cross-sectional studies, the cohort effects, particularly if you're studying age ranges that are very far apart. Then it's really, certainly society has changed between the time, those 40-year-olds were kids compared to today's 10-year-olds. And in a longitudinal study, you don't have to worry about that problem, because you test those 10-year-olds and their computer skills, and then you test the same individuals when they're 40, and what you would end up finding is that, they were all better at computers when they're 40 compared to when they were 10, because they've been learning their whole lives, and so they've added to their skills. And probably the 70-year-olds might even be above the 40-year-olds, or at least fairly equivalent. Just to finish up here, longitudinal designs are more powerful, but they take a lot of time and a lot of money to conduct that kind of research. Cross-sectionals are more quick and dirty. You can get the results cheaper and faster, but there's the potential of cohort effects, and the data is just not considered as compelling or as strong. Okay. A third type of developmental design is the sequential design. A sequential design basically just combines longitudinal and cross-sectional designs. I don't have a separate picture, but imagine that I start with that cross-sectional design on the left. I get a group of 5-year-olds, 8-year-olds, and 11-year-olds, and I compare them all. So I have a cross-sectional study right away. But then I also follow all three groups as they age. So in 2023, I would be comparing 8-year-olds, 11-year-olds, and 14-year-olds, because it's been 3 years later. So, and I would have a second cross-sectional design, but I could also compare them longitudinally. I can see how the 5-year-olds changed between 5 and 8, how the 8-year-olds changed, between 8 and 11. And then, I could follow all three groups again until 2026. So you could fill the numbers in here. There would be numbers in this whole 3x3 square. So you're following three groups, each of them, over a span of 6 years. So along the way, you get cross-sectional designs each time you test them. And you also have different sets of longitudinal designs. So you're getting multiple longitudinal and multiple cross-sectional designs in a sequential experiment. Once again, this is even more time-consuming and expensive compared to either a longitudinal or a cross-sectional alone. But it's a great design to gather a lot of data, and you get to do a lot of comparisons. Finally, we have a microgenetic design. This is like kind of like a mini, I think of it as a mini longitudinal design. I mean, you're watching a group of subjects as they acquire some new skill. So you want to look at the moment-to-moment changes as they learn or master that new skill. So an example might be, let's capture the moment when children say their first words, and like see what leads up to it, and see what they're like right after. And so what you would do is you would have a group of infants, and you would start watching them closely, like when it gets time that they might be saying their first words. Now, you may have to wait months, right? Because there's a wide range. Some children might just say the first words at 9 months. Other ones might wait till 15 months. But there are some indicators when they might be getting close. And so when they are close, you want to observe it when it happens. So you would have cameras, let's say in the home, that monitor the child over the course of weeks or months. So this is like a mini longitudinal design. You're watching some subjects over the course of time, but it's not for years or anything like that, because you just want to see a new skill develop, and so you can see the specifics of it. They've done this kind of thing, when for children about to take their first steps, they capture the moment, and so that they can see the exact behaviors leading up to it, and so any kind of new skill mastery or can be studied like this. Okay, and that is the end of video 4.